On behalf of Department of Electronics and Communication Engineering, R.M.D. Engineering College, and my own behalf, I welcome our eminent speaker of session 13, Mr.K. Manikandan, Staff Verification Engineer, Intel Corporation, Bangalore, to deliver the session on the topic Advanced Verification Methodology for Fast Computing Digital Design Circuits. My heartfelt gratitude for accepting our invitation to share your expertise among us amidst your busy schedule, sir.
Hi,
Thanks
ma'am.
for accepting, sir.
Yeah, thank you, ma'am. Thank you for your introduction.
I invite Srinidhi to introduce the speaker. Over to Srinidhi.
Let's introduce our distinguished speaker, Mr. Manikandan, who currently serves as a staff verification engineer at Intel Corporation, Bengaluru. Mr. Manikandan holds a bachelor's degree from Penang University, Chennai, and brings with him over 30 years of rich industry experience in the field of semiconductor design and verification. Throughout his career, he has been associated with some of the world's leading technology organizations. He has looked at the cooperation in both Penang, Malaysia, and Bengaluru, India, contributing to advanced verification methodologies and SOC validation. Prior to Intel, he served as a verification lead at Qualcomm and as a technical lead at Samsung Semiconductor India Research and Samsung Electronics, focusing on memory and high-speed protocols such as UFS, SAS, AXI, and AHD. His core expertise lies in functional and design verification using Verilog and UVM methodologies, along with deep knowledge of memory controllers, interfacing protocols, and hardware validation tools. With his proven ability to lead cross-function teams and architect complex SOC and IP verification environments. Mr. Manikandan exemplifies innovation and technical leadership in the semiconductor industry. Let us all welcome Mr. Manikandan, and he has his valuable insight and expertise with us today. We warmly welcome you, sir. The session is over to you. Thank you so much.
Yeah, thank you. Thank you for a brief introduction. Thanks, ma'am. I first of all have a great thankful for inviting me for this organization or for this event, right? Okay, let me share my screen and I'll go through it. Just give me a second. One second. Okay. Hope you can see my screen, right?
Yes, sir.
Okay. So yeah. So I think I will skip this slide because I got already introduction. So with me, like myself, Manikandan, I had the 16 years of experience in front-end ASIC design verification. So I have been working with a few companies in India as well as in Malaysia, right? So I've been a part of Samsung Research for almost 6+ years, and I've been in Qualcomm for a couple of years, and then for last almost 7 years, I am in part of Intel, both in Malaysia as well as in India, right? So this session I have planned such a way that I will start with basics of, like, I'll start with what is verification, and then we go into verification, and then I will go in what are the what we do actually, what we do in our real time, what we do, right? What is like what is system verilog, what is UVM, what is like how do we do, right? I think basic my from my side, right? I expect that participants will already have an idea of what is verilog, right? So with that, I'll go with system Verilog. I'll just give you the differences, right? How system Verilog is differentiated with Verilog, and from system Verilog, how we went for UVM and what UVM does, and then how we do verification. And at the end of the meeting, right? I mean, at the end of the presentation, I have some real example I can show with the EDA playground. So there is a place called EDA playground where you can go and do all your work, right? So I'll just show you the thing, how what we do and how it's all working, right? And one more thing is, right, here the session I don't want to be like more theoretical, right? I want, so wherever you anybody has any doubt, right, I just wanted to stop there and ask me and clarify it, right? So my intention is not to complete whatever I have and I had to go. It's not, that's not my intention. My intention is whatever, at least whatever I try to explain, right, I just wanted everyone to understand it so that you will have a good knowledge on what it is and how to implement, so that at the end of the session I expect you guys can go and start work on EDA playground. You can start write your basic some codes and you can verify, right? So that is the basic expectation from my side. So I don't want to just go theoretically and explain blah 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 and finish it. That's not my expectation, and I am also not that type. So any doubt at any slide or any point or whatever I explain, right? Please stop me there and just ask me so I can explain it, right? Okay, fine. Let me go over it, right? So let me explain about what is digital verification, right? Digital design verification, what it is all about. Okay, so what is verification, right? What we do, one second, I just try to minimize this. This is blocking, right? Okay. So what is verification, right? What we actually do. So basically, verification is nothing but, as the name says, right? We are going to verify the digital circuits, whatever circuits we are designing, right? We are going to verify it. Say from basic, from an AND gate till the complex, whatever SOCs we have, right? In today's world, it's for data center or it's for a AI or it's for any application. The big SOCs what we work today. So it's all we are going to verify from basic to SOCs, right? So that is what your verification basically it means. So verification is nothing but it's a critical process of ensuring a chip design is functional and meets all the specifications before manufacturing, right? So we are going to make sure that whatever functionality that chip is going to execute, right? We want to make sure it's working before it goes to manufacturing. Manufacturing in the sense before it goes to silicon, what we call as silicon, right? Once it is in silicon, right, we cannot do anything. Once if there is any issue, it's all done. We cannot fix any issue in the silicon, as you guys know, right? So we have to go for the respin. So that costs very high, right? So this is what the basic verification means. So why it is very essential? Why we want to do it? Why, like, what happens if you don't do it? So in the real world, right? So we have complex circuits and systems, which is challenging and intricate process, right? It's easy to get caught up in the design itself. It is equal. So what it means here, right? So we can get if it is a simple logic circuit, right? Simple combinational circuit or simple multiplexer or adder, right? We can get in the design itself. So module to end module, whatever you write, you can get it. But whereas when you go for the big IPs or when you go for SOCs, right? We cannot. It's not that as easy. You can get it in the design. So we need a proper environment to make sure to verify all the functionalities. Let's take a small example, right? If you take an memory circuit, right? So you have a memory. What is the purpose of that memory? The memory is like you are going to write and read to the memory. So that is the basic purpose of the memory. So as a verification engineer, right, if that memory circuit, like that memory is been coded as a design and give to you, so what we are going to do is we are going to make sure that we are able to access all the regions inside the memory, whether we are able to write all the regions inside the memory, and when you read back whatever you are written, right, we should able to get the same data. Then only we can say the memory is proper, right? If you read some other data and like you write, for example, you write 1 2 3, and when you read back, when you get some other data, right, this is a faulty circuit, right? So we want to go and debug and see why the data is mismatching, kind of thing, right? So if you don't do at this verification, right, see, this one comes along with your design. So I think last presentation, right, he would have explained, right, the stages, right? First will be the circuit, like RTL design, where you code your design will be coded. Then comes your verification, which runs parallel to your RTL. So whatever the design is done, then and there we will do the verification to make sure that design meets your spec. So whatever is in the spec, it's in the design, and in the design, whatever is there, it will be in the verification. Will map it. If you miss any bug in the verification, right, then it goes for the pre-silicon, and then it goes for the gets, right? That's what he explained last time. So it goes for timing, power, and it goes for the netlist, and then finally it goes for circuit, right? So if you miss a bug at this point, it's very tough to find out the bug at the later stages. And if you find the bug at the later stage of the cycle, right, it's gonna be a very tedious process. Say for example, right, in our SOC, we take minimum 3 months for a design a particular IP in SOC, and we spend almost 6 to 9 months for verification. After that, it goes for the physical design, where he explained, right, the timing and all the static timing, the closure, and then it goes for different process. Finally, it goes for silicon. So at the end of the silicon will come after 1.5 years, right, or 2 years. So after your silicon, you go for the post silicon validation, you find some bug, right? So whatever you did for 2 years is wasted. So again, you have to start from the scratch, right? So the 2 years of time with so much of energy, so much of money involved in it, so it's gonna be waste. So it's been advised that we have to find the bugs as early as it is, okay, to avoid thing. I have few examples. I just want to go through very fast of this. This is a very small thing. what are the errors we get it, right? So usually we get the human error, right? What are the different type of human errors we get is sometimes we get the conceptual errors. So this happens in our real time, right? Anywhere, right? Not only in our design, right? In any place, right? So you will given a concept, but when the design engineer is reading the spec, right, he would have misunderstood the concept. Say for example, instead of implementing USB 2.0, if he had some problem, if you have went for the USB 3.0, right, then it's a concept error. From the spec, it is mentioned that they will support USB 2.0, but when the design is implemented for USB 3.0, so it's a concept error, right? So it's after that when you test for USB 2.0 function, it may or may not work. So that's a problem. So these are the basic errors what we want to make sure that we will not have it. Then we have the logic errors, the logic how you implement, right? Say for example, you want to implement an AND gate, right, which will be like as in C is equal to A and B. Instead of that and ampersand, right, if you put R, right, it will work like a OR gate. You think that you have implemented AND gate, but the functionality will be an OR gate. So it's a logical error. This looks very simple, but when you go into a real-time circuit, real-time design, right, it will give a very big issue, and you will not know the error is due to this one. Because at the end of the SOC, right, finally you will find some data will be mismatched, or some data will be corrupted, or you will not receive the data, or you will not receive the packet. But why it is happening, right? You have to debug from there, you have to debug. Finally, you end up at this point where you would have did some instead of and you would have did an or instead of or you would have did some other logics, or instead of doing in the case statement, instead of assigning a value of 0 1, you would have assigned a value of 1 0, kind of very basic error. But this one you will able to debug at the last, where from it will be like you will be missing a packet. That will be the error. Why the packet is missed? You have to debug, and you have to come and end up like this. So when the code is done, we have to be very careful, make sure that we don't do any logical errors. If there is any logical errors, we have to find it in verification. It's very tough to debug in verification, right? But even if you miss in verification, right, this bug to debug after the post silicon, it will be very tedious job. You cannot do that. Okay, so that's why we do this verification. And then there might be some coding errors. Then we have some timing errors. As he explained, right, there will be some setup time, hold time violations. If you miss all those things, it will, these are the few common errors what you see. Okay. And the cost of undetected errors, right? What happens when you don't detect the error, right? How much cost you want to spend? So there are multiple things. One is financial cost. Financial cost is for, see, you want to do the rework, and once, as I said, right, if your chip is done, you cannot do anything. So you have to do everything to be redone, rework, and then you do want to do a respin. So the entire cost spent for that is very high. It will be in like billions of dollars, right? So that is waste. Second thing, it's your silicon is manufactured, right? That silicon is wasted. Then you will be delayed to market. See, for example, the product is being expected to come in the market by 2025, but at the end of that, by the time the product is out, you find that it's not working, it's having any issue, right? You have to throw that, and again you have to do it from the scratch. You will come to the market by 2027. By the time your competitor will be already in the market, you come in 2027, no one will take you, right? Say for example, if you want to make 1 GB memory, right? So 1 GB SD card you are making. So your plan is to make by 2025. So you have competitors, right? So for example, Samsung, Intel, and there are other few companies, they are making it, right? So 2025, if everybody is making that, then there will be a competition equal for everyone. But for example, if there is a product from Samsung which has been buggy, right? By end of 2025, he is finding that 1 GB RAM what he has made has some problem. Then he cannot come to the market. So he has to do it everything. He has to come again after 2 years by 2027. So when 2027 when he comes to market, right, his competitors will be already with 2 GB RAM or 3 GB RAM. So this one is of no use, right? This is wasted, right? So you will lose your market. You will lose your share in the market, right? The product share will be lost, and then there will be loss of revenue, right? Obviously, when you lose your market, there will be loss of revenue. And if there is any, see, for example, if your chip, right, if your IC is going and sitting in your medical equipments, right, or if it is in any aircraft kind of thing, right, if it doesn't act, do the actual functionality, if there is any bug in the chip, and if the functionality is wrong, right, it will cause lot of death, right? And then we have to have some legal liabilities and all those things, right? So there are a lot of issues on those things. So to avoid all this, we need to do verification at the beginning, and we have to do very deep verification. That's why we have a very what you call very explained or very detailed way of doing it, right? It's not that come do something and go. It's not that way. Very structural, very standard way, very procedural way we are doing it. I will explain all those things, right? I will go and explain one by one, right? time is, as I said, right, there will be a small error like AND gets replaced by OR gate, but that you will find at the end of the simulation, you will find that there is something is wrong. So you have to debug from there, right? It takes minimum 1 day to debug, and finally you will find there is small mistake. Instead of AND, it will be OR, but that you will find at the end of a day. Like this, in a big circuit, if you make hundreds of mistakes, right? Minimum, like as I said, at 100 days, right? 100 days nothing, but your 3 quarters is done. Things 1 quarter is done already. So you will be delayed to the market, right? So all those things will take a lot of time. So we have to be very keen in doing our verification. Okay, so if you, as I said, right, you will lose your if you don't do proper verification, right, you will lose your customer trust. Then they'll, in the market, right, they'll tell that, okay, Samsung memory is not good, Samsung phone is not good, because it's all because of the bugs what you miss at the verification stage. So it will give your trust will be gone, the brand image will be gone, all those things will be there, right? Okay. And then there will be safety and reliability, as I said, right? If you are implementing many critical features, if there is any problem, then it goes to your safety measures. If it is a problem in the phone, it's okay, it's fine still, only money is lost. Whereas when you do in aircraft or in healthcare, right, if there is something problem, then it's all due to very critical applications, then there will be a lot of legal liabilities you have to see. Okay. Okay, let's go with here, right? From here, I just wanted to be very technical things, right? Okay, let's go with system Verilog. Right? What is system Verilog? I don't know how many participants are already aware of system Verilog. If somebody is aware, it's fine. If you are if you are hearing this term system Verilog for the first time, that is also good. Let me explain you from basic, right? System Verilog is nothing but an extension to the Verilog language. The Verilog is the hardware descriptive language, right? HDL language. To that, we have something called extension of that. We have system Verilog. System Verilog was developed as an extension to Verilog to address its limitations and expand its capabilities, especially for large and complex verification projects, right? So earlier, before System Verilog, the design was in Verilog. The test bench also was in Verilog only. But what happens when the design gets complicated, right? When the design gets more and more and more complicated, right? Everything we were not able to verify within only with Verilog, right? Verilog had only limited features. With that capabilities and with that limited features, we were not able to verify everything, right? So that's why we went for the system Verilog. So what it does, right? It incorporates Verilog's capabilities, but also adds new features, right? Basically, I can say simple way, right? Verilog plus OOPS concept, right? Whatever object oriented, right? When you add these two, basically form system Verilog. And additionally, we have some more features. I'll explain those features later. So if you see the overall, right, Verilog plus your OOPS concept, object oriented OOPS concept, you will call it as a system Verilog. Okay. So what are the advantages of system Verilog, right? It is a superset of Verilog. So what all Verilog supports, right? Everything will be supported in your system Verilog. Okay. Then it has enhanced verification features. It has OOPS oriented, like object oriented programming, like OOPS concept it has. So I think the participants will be aware of OOPS concept, right? I'm not going to explain the OOPS here in detail, right? It's all that whatever you have, the inheritance, polymorphism, abstraction, encapsulation, what all you have in OOPS concept, right? The way you create a class, how you declare an object, and how object is instantiated, how it is being used in a virtual method, everything will be there in the system Verilog. Okay. So if you are not aware of OOPS language, please go and refresh with OOPS language, right? Because this session is not for that. Okay. OOPS will integrate the OOPS concept here. And then we have something called randomization and constraints. I'll explain what is randomization and constraints, how you do this random and constraints, what we do, how we do, that we'll see. And then we have something called assertion-based verification. I'll also explain what is assertion-based. I will also explain coverage-driven, right? What is coverage-driven? What is coverage driven verification? And then we have something called interface and data tips. I'll explain everything in detail, right? So before this, right, I'll just tell you, right, in base, like overview of what is coverage driven, right? See, I have a circuit, right? Let me take in a real time SOC, right? I have an SOC. I will do verification, right? I'll do verify, right? I will be verifying that for n number of days. Every time I verify, I might find new bug, or I will try to verify, right? But in the real case, right, we need a point to go and stop the verification, right? We need to stop. Okay, I am done with the verification. It's enough at this point. I need to stop. But how will you stop? How I know that I have done extensively my verification? My design is full. Like I don't find any more bugs in my design. There is no more errors in the design. So how will we come to that conclusion? We'll come to that conclusion based on coverage driven, right? So we have something called coverage. So we have something called code coverage and functional coverage. I'll explain those things in later, but I'll just give you, right? So we have something called code coverage and functional coverage. We want those metrics to meet 100%. Code coverage should be 100%, functional coverage 100%. So, but practically code coverage may not 100%. We might hit to around 90, 95, and then functional coverage should be 100%. So once you hit these numbers, right, then we will come to some uh, confidence that our circuit or our design is fine. Then we can go to the next step. So that confidence will be got only in the coverage. So what is that coverage? How will you do? I'll come to that later point, right? So these are the things we will do in our verification, right? Okay, so this is some basic difference between your Verilog and system Verilog, right? What does Verilog does and what does system Verilog does? So I just show you this, but I don't want to go in deep and explain everything, right? If later I can share that PPT, these are basics you can also go through, right? Okay, so it's a oops, it supports system Verilog supports, whereas in Verilog it doesn't support. You don't have assertions in Verilog. In system Verilog we have coverage. It's not very limited here, but here we have coverage supported. That's what I said. Functional coverage, code coverage, all those will be supported for system Verilog. And then it's what is program blocks and all. I'll explain you, right? Later I'll explain you in this slide. And then it cannot handle the complex design, right? Where system Verilog we can handle the complex design. And then modularity is very limited modules we can have. Here it can verify any complex SOCs we can be done in system Verilog. It's for very basic design only we'll use Verilog. This is for full design we'll use system Verilog. Okay, so this thing I think I'll share. You can check each point by point, right? So I don't want to waste time over here. It's all theory only here. Okay, so basically a verification, right? What type of verification we do in our real time, right? So basically we have two things. One is functional verification, another one is non-functional verification. So what do you mean by a functional verification? So functional verification means we are verifying all the scenarios of a functional of an IP. Say for example, I have an USB, right? USB, I have an IP. So what are the functions I need to check for the USB IP? So whenever I connect the USB, right? For example, I connect my USB to my laptop or my processor, right? The first thing it has to be detected. So that is one scenario. Second thing is whether I'm able to, if it is a 2 GB USB, whether I'm able to access write into the full 2 GB I'm able to write, and what that's another scenario. Whether I'm able to read all the 2 GB, that's another scenario. What happens when I write only 5 MB? What happens? What happens if I write only 10 MB? Those are different scenarios. So what happens? This is called functional verification. We are going to verify each and every scenario of that USB. That is called a functional verification. What happens if, for example, when you're copying a data, right? In between 2 GB data when you're copying, in between, if I remove my USB, what happens? If I suddenly hot plug my USB, what happens? These are the scenarios, right? These are all comes under a functional verification. What comes in a non-functional verification? Say, for example, that USB IP consumes 5 volts, right? So 5 volts of power. So the design should consume only 5. Whether it is consuming 5 volts or it's consuming more than that, or it is only 10 millivolts or more than 10 millivolts, and how much area it occupies, right? We say about it's in place, for example, 100 million gates, or whether it is in 200 million gates. So whether it is in the beginning will tell, okay, this is going to be this much of size, whether our design meets that size or not. So that can be, those things will verify. And timing, right? How much fast it is. Timing is nothing but my USB works with 2 megahertz or 2 gigahertz speed, 5 gigahertz speed. So is it really working in that speed, or if it is working less speed, or it is working more than that speed? So all those things will be verified in the non-functional verification. All the futures, right? Whether you are able to write or read, all those things will be done in your functional verification. Okay. Sometimes what happens, the functional will be you can able to write and read, but what happens if, for example, you say that your USB is going to work with 5 gigahertz speed, but at the end of your write and read, if you see, it takes it is less than that, right? It takes 2 giga, it works in 2 gigahertz speed, then your design doesn't meet, right? So it's a non-functional bug. Your design doesn't meet. So you have to come and optimize your design so that your write and read is fine. You can able to write and read, but your speed didn't match, or if it consumes more area. So that's the problem. So you have to come and optimize your design so that it will take that less, it consume less area. So all those is a non-functional verification, right? So we have something called functional verification, non-functional verification. Okay. And Next we have, right, in now we will see functional verification, right? In functional verification, we have different types of verification. One is directed, another one is random, and another one is coverage driven. So what is a directed verification, right? So direct verification is thing, but we will have some directed test cases, right? For example, out of 2 GB address, right, I'm going to target to address, say, for example, address 1000. This is the address I'm going to target. So what happens? My test case will have that address, and I'll give directly, I'll target that address, right? So that is called a directed test. Whereas in a random verification, right, what happens? The test case what you write will have a random address generated from 0 to 2 GB. It will be generated some random address, right? Because we have to make sure that we can able to access any address of 2 GB, right? So we'll go for random generation. That test case will generate a random address and random data. It will check for all the data's random data, right? So and another one is a coverage driven. As I said, whether we are able to make sure that we have functional coverage and code coverage 100%. Okay, all those things I'll show with examples, right? So that you will get an you can able to map what it is. Before going to that, I just want to give you the terms what we use, right? So you should know all the terms what are we have and we have in our verification. Now, in system Verilog, right, I'll just tell you the basic things, right? How it differs from the Verilog, right? In Verilog, if you know Verilog, right, you would have gone and seen the Verilog code, right? Verilog has something called wire and register. For example, when you declare a module A comma B, then inside that you can write wire A, wire B, right? And you have something called register. So you should able to identify when you have to give wire, when you have to give registers, right? So all those like concepts will be overwritten in system Verilog by using a logic. So in system Verilog, we don't have the concept of wire registers. We have only logic. Logic can be wire, logic can be a register. It's a data type, right? That data type can be a wire or register, doesn't matter. So we'll give a logic, and logic can be a 4-state, right? What do you mean by 4-state? Which means it can take the values of 0, 1, x, and z. So if I declare a value like logic A, means logic A can be that A can be 0, it can handle value of 1, it can handle the value of x, it can handle the value of z. So that is a 4-state. And there is something called logic, right? That's not what we said, logic signal. And we have something called the logic 7 down to 0 byte, right? If you want to declare a variable which is of 8 bits, so we'll declare like this 7 down to 0, which means it's a 8-bit variable. And it can be a wire or register, we don't matter. So it's a logic. And then we have something called bit. This bit is not there in your Verilog. We don't have the concept of bit. In system Verilog, we have something called bit. Bit can be a 2-state variable. Bit, if I declare bit flag, right, this flag variable cannot handle x or z. It can handle only 0 and 1. If you drive x or z, right, for example, if you assign x to this flag, right, it will give an error at the current time because bit is a 2-state. Bit cannot handle the value of x and z. It is only 0 and 1. Bit 15 down to 0 of data, which means this data variable can handle only 0 or 1. It cannot handle x or z. Okay. And there is something called integer. Whereas in Verilog, we have only int. Here we have an integer. Okay. It's a signed 32-bit. Integer count equal to 0. Means it can store 32-bit value into this. Count can be 32-bit. 32-bit means it's like F. So that much bit it can store. It's a 32 bits. Okay. And int has short int, long int also. Okay. Short int is, if you want to use only 16-bit, then you'll go for short int. If you want to use long, like 64-bit, then you go for long int. The declaration of the data types, right? And then we have something called type def, enum. Okay. And okay. So then we have something called initial block. This is very important. This one, I don't think so we have in Verilog. Even though you have in Verilog, we may not use mostly in Verilog, right? So you use in system Verilog. So what is this initial block, right? So in your Verilog code, right, module, end module you have, right? In between the module to end module, you will put something called initial block. Initial, begin, end. So inside this, in between this begin, end, you can write anything, right? Whatever you write in this, right, whatever code you write, this will execute at the 0 time of the simulation. In simulation, right, it will start with 0 nanosecond, then the simulation goes 0 nanosecond, 1, 10, 50, 100, it will go on, right? Whatever you write inside the initial begin will happen at the 0 nanosecond. Okay. So that's why, and we can have multiple initial begin inside your one module to end module. Module to end module, you can have initial begin end Then we have one more initial begin, and we can have one more initial begin, and we can have multiple initial begin end statements. The only thing inside this begin end, right, we cannot have anything which takes time, right? For example, hash delays, or you are waiting for something, right? So those things you cannot have. Okay. Other than that, you can have anything inside your begin and end. And other control flow constructs, these are similar to your Verilog. You will have if else, you will have case statements, you will have loops. These are all similar to your Verilog only. Okay. And then I'll show you a basic of your oops, right? I will not go in detail, but I'll tell what basic what we have, right? So this is a class which is going to have a packet, right? I'm going to have the packet class, right? So this packet, what packet it is? It's some memory packet which is going to have some address and data. I'm going to write some data to a particular address. So it has some address and data. And we have some new, the constructor, right? I remember you guys know, if you know oops, you will know, right? Any object you have to construct, right? You have to allocate the memory. So function new int a comma d, which is the constructor for this address and data. Address equal to you a and data equal to d end class. Now you want to create the object, right? Now you allocate the memory. Now you have to create that memory, right? So you create packet p1 equal to new of 10 and 20, which means a is 10, d is 20, which means address is 10, data is 20. Okay, like this. And we have this inheritance and polymorphism also, right? This one small example where you have base packet and you have some function over here, and you can extend that base packet here, right? Extend that packet, and then you can call that function, whatever process you have, right? That you can call here void process. Here you don't define here, then you can define it here. Void process display processing extended packet. So these are the things is basic oops, but how, like, you have multiple applications of it. Say for example, I'll give a small example, right? You have a USB IP, right? I'll go with USB because USB, it's very common for everyone. So I'll take that example every now and then. So you have an USB IP, right? So what happens? I have an USB IP, but that USB IP functionality depends based on my application. Say for example, that USB IP goes for a laptop. It goes for a normal processor, right? Desktop processor. It goes for it. So when you want to connect that USB IP to my laptop, right? I wanted only say 3 functions of it. Say for example, the USB IP, I may not want the hot plug. That function I don't want, but I have few functions common, right? Your read and writing to the your USB, reading to the USB, it's common. So what happened? I'll put it in the base class. So write function, read function. My application differs, right? When I am going for USB in laptop application, I can just use that IP. We'll call that IP as such, but inside that I will add one more new feature called hot plug. Whereas when I go for desktop, what happens? I'll call that IP when when I am instantiating that IP, right? I will get write function, read function. In addition to that, I will add one more function, detect. So that is a new function I'll add in my child class. So all this one, right? When you go for the real time, you will get a lot of applications. This is just a small example I gave, but you have to imagine how it works in the real time. Okay, so then we have something called random variables, right? So as I said, right, random earlier, I said, right, random verification. I said somewhere, right? Okay, random verification, right? So what we do in this random verification? Okay, so I have something called random variables, right? So here, what I declare, right, inside my class packet, I have address and data, right? This address, as I said, this is an integer, right? This is, since it's an int variable, it can have any value, right? Address can be 0 to, say for example, I'm going to have, as I said, 2 GB RAM. So I need to measure, I need to have 0 to 2 GB address I need to have. So I need to test all the addresses. 0th address I'll write and read. First address, second location, third location, like that. 2 GB, the like last location also I need to write and read. In that case, if I have one test case to read and write from 0th location, then one more test case for first location, and if I have one test case for 100th location, like this, if I have, right, I cannot have 2 GB test cases to measure, means to verify all the locations, right? I cannot do that, or I cannot put any address, right? So what I do, I'll declare it as a random address, right? So what happens when I put the variable rand? This is a keyword, system verilog keyword, right? Rand. I'll declare as a rand address, and the data also I'll give any random data, rand data I'll give. So what happens? I'll make sure that data and address can be anything. Now, if I want to make sure this address, right, I don't want to verify 2 GB. I want to only verify, for example, in this case, they are taken 255, right? If I want to verify only 256 locations, what I need to do is I need to constrain that out of that, because this address can be any variable, right? It can take any address, but I don't want, I want only 256 locations only. I'm going to verify only 256 location. What happens? So I need to write a constraint. So constraint valid range is address should be greater than 0 and it should be less than 255. Okay, and then data, I'm going to take only even bits. So data mod 2 is 0, and then I'll randomize this packet, right? P equal to new, then I call this function randomize. This is a built-in function. So when I call dot randomize, this is a built-in function. This will be automatically randomized. So when I call this function, what happens, right? So I have one test case and I'll run the test case for 100 times. That also I can automate. I will put one statement, right? Run test case 100 times. What happens? 100 times it will run, 100 times it will randomize. So every time when it randomizing, right, this address value will be a different values. First time will be 0, next time will be 10, next time will be 20, next time will be 37, next time will be 49, 255. It can be anything, right? So if I run this, like, I'll just automate the test, right? I'll just run the test case for 100 times. So I'll get, after 100 runs, I'll see I would have one test case ran for 100 times, would have targeted 100 address. If I don't have this keyword, right, what I should have done, I should have done 100 test case I have to write, and I have to run all the 100 test case one by one. Test case 1, test case 2, test case 100. I have to run like that. But in real time, we cannot do all those things, right? So what we do, we go for the something called random. So this keyword is called random. And there is one more keyword I think I didn't put over here. Say, for example, right, here, as I said, if, for example, I do that randomize for 10 times, I run the test case, right? 10 times I'm running the test case. So that 10 times, right, I can get out for 10 times, I can get 10 different address. For example, 2, 3, 10, 100, I can get 10 different address. Or I also get same address for 10 times. Say, for example, address 10, I can get for all the 10 times I would have got under, like, same address, 10th address also. That is also possible. It would have randomized it, but the random output can be anything, right? So first time it got 10, second time also it can get 10. So if I run 100 times I would have got 10, right? So that is also possible. So in that case, what happens? We would have not verified 100 locations. We would have verified only one location. Though you ran for 100 times, we would have verified one location, right? So to avoid that, right, we have one more keyword called rand c. We will put here next to rand, right? We put rand c, which means rand c is nothing but cyclic. C stands for cyclic, which means you run for 100 times. It makes sure it will not generate the value which has been generated already. So first time it will generate 10. Next time it makes sure that it will generate 20. Next time it makes sure it generates 37. Next 49, something like that. Okay, so that will be used. Rand C keyword we can use. You can use rand, or if you want to make sure that you don't want to generate the already generated values, then you use for the rand C. Okay, rand C method. So there are two types of random variables you can use. Okay, so before that, right, any queries or any questions so far? Or if I'm going very fast, please let me know. I'll just give you 30 seconds of time. If anybody has anything, any questions so far what we seen, just let me know. Or else I can continue. Okay. I think you guys can understand. Okay, I'll go to the next slide, right? Next, we have something called interface. What is the interface, right? This is like, imagine we have you take any say, for example, I take an HDMI, right? Okay, you take an HDMI cable, right? In the HDMI cable, if you see, right, you will see the pins inside HDMI cable, right? You see some pins. You take a VGA cable, you see some pins, right? So those pins are real, like hardware interface pins. But whatever we do in our case, it's all simulation, right? So we have something called software, right? So here we call the pins, right? We have called it as the interface. So in our example, the address, data, whatever we have, right? These things we will declare inside an interface. So interface has something called the data, address, valid, all the pins what you have in the hardware, right? Those are called pins in your interface. Okay. So that is called interface. And this is how you connect your interface, right? You have an interface which has clock, data, and then some valid. and then you can connect b dot valid is nothing but you can display, if valid is 1, you can display this data, something like this. Okay. Okay. So I said you about something called coverage driven, right? So I'll give a small overview, right? What is coverage driven? Say, for example, I have a functional coverage, nothing but I want to make sure that I have verified all the features of my design. Say, for example, if I take my design, right? My design has, as I said, I have a hot plug is a scenario. I have a read as a scenario, write as a scenario. I have read enable as one scenario. So I have multiple scenarios, right? Whether I have verified all the scenarios, I cannot go and say to my manager, right? Even though I didn't verify, for example, I didn't verify the read scenario, but I can say to my manager that yes, I have verified all the features. He don't know how, like he doesn't know whether I verified or not, right? If I say, he has to believe. But what happens actually in real time, right? We have some metrics called coverage metrics. I cannot lie to the metrics, right? That is generated by the tool. If I run, it get generated. I cannot generate it. It will be generated automatically if I run the test case, right? So that where we have this coverage group, right? Say, for example, why we are having this, right? As I said earlier case, right? We'll go with this example address. So here we generated the address 0 to 255. Okay. So I want to make sure whether I have like I have ran my test case to make sure that I have covered the initial regions, like for example the start regions, right? 0, 1, 2, and whether I covered the last regions, whether I covered in between regions. How will I come to know? I will have something called cover group. I will add a bins like this. These are called bins 0, 1, 2, right? This is because when I run my test case, right? In that test case, the random address, right? If it was generated address value as 1, then this bin will hit. Okay. So if I run for 10 times, out of 10 times, I have generated only the address 0, 1, 2, 10, 20 or something. I didn't generate the address, this address if I have not generated, means my metrics looks like I covered only 50%. My coverage will tell I have covered only 50%, not 100%. Then I'll go and look into the report. Why only 50%? Then it will tell whatever values you mentioned here, it's not generated in the test case, which means that random test has not generated the value for 253, 254. So what I need to do, I have to rerun the test case for some more time, more number of times. So 100 times, I need to run for 200 times. So I will get some value out of this 253, 254. If I get any value out of this, then this also will be covered. Then if I'll get 100%, I'll show this to my manager, say, sir, for the variable address, I have 100% coverage, which means I have covered this, whatever value we have mentioned here, I have covered whatever mentioned here. So my test case has covered it. What does it actually means? I have given the 0th location to the memory that design, and I'm able to read and write from the 0th location. There is no issue in that. I'm able to give the address 253. In the 253 address, I can able to read and write. There is no issue. So this 100% of cover group will give me the confidence saying that this particular design has been working for this particular value. This value I gave as an input. For this particular input value, this design has worked and I got 100% as my coverage report. So this will give you, this will tell my boss like this. We have cover group, like multiple cover groups. I can show one real time example in our real project, right? So we have multiple cover groups. So you have to get 100% in finally. So if you get 100%, then means it will tell, okay, 100% you are covered. Okay. And same thing, we have something called code coverage. What do you mean by code coverage? Is that the design, whatever we have written, right? It has to cover everything. Say, for example, the code coverage will have multiple coverage, right? Line coverage, block coverage, FSM coverage, toggle coverage, multiple coverage. What does it say? Line coverage means all the lines inside my code has to be exercised. If I run a test case, it has to hit all the lines of the code. Then only it will give 100% of line coverage. Same way, if I give, for example, there was an if else, right? I'll just show. Okay, I have an if else, right? Okay, there is a if else, if enable output equal to input 1, if not output equal to input 2, right? In my test case, right, this is a circuit, right? For example, this is the design we have. This kind of mux. When you have enable, output will be this one. If enable is 0, this will be the output. So when I am verifying, right, I am always giving enable 1 only. Okay, enable is a value of 1, and my circuit is always working. There is a problem when enable is 0, it input 2 is not coming to output. It means I am not connected this input 2. If that is a case, if I will always give enable as 1, this circuit will always work. I will not find any error. But if I go and tell my manager, right, I verified it. How come he comes to know? He will come to know from the code coverage. He will see the code coverage will be generated. After running all my test cases, right, there will be a report generated saying that in this statement, the test cases has already, like, it is exercising only this statement. The else part has never exercised, which means none of my test case had the value enable equal to 0. I never tried enable equal to 0. So he'll come and ask me, why you never tried enable equal to 0? You have to go and try that value. So then I have to create one test case, write a test case, give the value enable equal to 0. If I can give enable equal to 0, then I'll come, then this will be exercised. In that case, if there is a problem in this into, then we'll come to find, okay, there is an error. If not, it will work fine. Same way with case statements, right? Every time if I give opcode as 0001 and I didn't give the 0010, if I never give, right, that code coverage will not be 100%. The statement, right, the case statement will never get 100%. It will get only 50% or 80%, 75%, depend upon how many statements I have covered. Okay, so that is the thing. So these all are the some of the reports. So if I get 100% code coverage, 100% functional coverage, then only I'll tell my verification is done. I can close my verification. Okay. Okay. Next we'll go for something called, this will be coverages, right? I'll show that later. We have functional coverage, code coverage, and then we have some tools to generate and show you how coverage reports are generated. So far we have seen the system Verilog, right? Next we go for UVM, right? Why I want to go for UVM, right? What is UVM? Why I want to go for UVM, right? See, the verification, you can verify a circuit in any way. You can verify a logic in any way. But in real time, right? If, like, I have my own way of verifying, right? So same with you, right? If I ask you to verify, for example, I give you a FIFO, right? I give you a FIFO. I'll ask you to verify the FIFO, right? You can verify in your own way. I can verify in my own way, right? Say, for example, FIFO, first what I do is I will write all 10 locations. After that, I'll read all the 10 locations. You will, what you do, you write first location, read first location, write second location, read second location. It's a type of verification what you do, right? So each one will do it in your own way, right? But in real time, we cannot do that way, right? I cannot do my own way. You cannot do your own way. Why? Because if I do my own way, and if I'm, for example, I verify FIFO in my own way, right? I write my own driver code, I write my own sequencer code, and then I leave my company. If somebody comes to the project, right? If he comes and sits and see, he cannot understand my code, he cannot understand. Or if I want to understand somebody's code, right? I cannot understand somebody's code. I cannot see what he had done, where he connected what, or how the data goes from this module to that module. We don't know, right? For that, what they do is, industry, right, all over the world, they came up with a common methodology that is called UVM, Universal Verification Methodology. You want to verify any circuit, be a small AND gate, or be an IP, or be an SOC, or be a core, whatever it is, right? You have to follow this method. You have to follow, there's a proper structure for it. This has to be done here, this work has to be done here, this part has to be done here, this part has to be done here. So like this, we have fixed things. You have to go and do that only. You cannot do as you like. Okay, so that is called UVM, right? So in UVM is nothing but the structure, how the, what you call that, overall structure, right? That is UVM. In that, you write the code which is in system Verilog. System Verilog code is written in UVM, and UVM has some structure. Okay, I'll have this here, I'll have this here, I'll have this here, right? So that is predefined, and you have to follow that. That is called your UVM. Let's go with the UVM, right? I'll just give you a brief introduction. What is UVM, right? UVM is nothing but that verification methodology which is adopted everywhere, right, in system Verilog, and it has been coded in system Verilog. It provides a standardized methodology to reusable and modular test benches, right? What do you mean by reusable, right? What is why I want to do reusable code, right? For example, I have a block. Say, for example, I have a FIFO. Okay, FIFO, I have a block. This FIFO can be FIFO, I think, right? You know, right? First in, first one, like a FIFO. So this FIFO can be implemented in multiple applications. For example, FIFO can come in an USB IP. FIFO can come in an SerDes IP. FIFO can come inside your HDMI IP. FIFO can come in another RAM IP. It can come in different IPs, right? So what happens? I cannot have 5 engineers. Like, for example, one engineer is working on USB, one engineer is working on HDMI, one engineer is working on display port, right? I cannot ask HDMI engineer to write a FIFO, and again another guy who's working on USB, I cannot ask him to FIFO, right? I cannot ask everyone to write the FIFO. What I do, right? I will ask one engineer to write FIFO. That FIFO code, I should be able to reuse it in all the IPs. So I should write a code such a way, and same way the verification environment also, right? That UVM environment, what I created for FIFO, I should be able to use it. If I take the FIFO, I wanted the FIFO functionality in USB, right? I will use this FIFO environment. Whatever I had, I can directly reuse it in my USB. I can directly reuse the same environment in my HDMI. I can reuse it in whatever application I want, right? So that's where your UVM comes for. You can just reuse it wherever you want. You write one thing and you can use it. Same way, the HDMI is one IP, right? When you go for SOC, so you take your laptop, right? This is an SOC. In your laptop, right, you find multiple inputs, right? You see your power, you see your HDMI port, you see your what do you call it? You see your USB port, you can see your audio port. You see multiple things, right? You might have a CD port. You have multiple inputs, right? So all this is connected to an SOC. So in now I have a USB, right? USB, I have a verification environment. If I going to verify the laptop as an SOC full, right? I cannot go and write again the USB environment. I cannot write for laptop, right? What I do, I just reuse the USB. Whatever I done for the IP, right? I will reuse it in my SOC kind of thing. Block, IP, SOC. So whatever written in the block should be reusable in IP. Whatever is written in IP should be reusable in SOC. So that future, right? That functionality can be achieved in your UVM. Okay. So that is the main thing. Like standard, it's a standard one. You can reuse it. It is scalable automation. And advantages is it can accelerate. It can like whatever I explained, right? So it is usable across different SOCs. All those are advantages. Now, how the architecture looks like, right? What as an UVM architecture, how it looks like. Okay, so there will be something called test layer. Okay, so just for now, you just know the names of these things, right? Later, I will explain you what it all means, right? Test layer. We have something called environment layer. We have something called agent layer. We have interface layer, DUT layer, right? Whatever test cases I am writing, right? So all the test cases should come inside my test layer. I cannot write my test cases inside my environment layer. If I write my test cases in environment layer, it still will work. It will work. There won't be any error. But the thing is, if tomorrow someone want to come and check my test case, right? He will go and check only in the test layer. He will not check in the environment. He will check in the test layer, and if the test case is not available, he'll tell that test is not available. But the test will I would have done in environment, right? So that is a wrong way. So that's why we call each one has to be done in its own place. Okay. Test layer has to be done. Test case has to be done in test layer. Environment means we have some agent, monitor, driver. I'll explain you what is each agent means, what is driver means, right? So you have agent, driver, monitor, right? All this will be in the environment layer. And then we have this, whatever you have this agents, right? That will have the stimulus generation in the agent layer. And then interface, right? Where you connect your actual DUT, your test bench, right? Test bench will be a different environment and your DUT will be different. We need to connect both the things, right? So that will be done on your interface layer, and that is a DUT where you have your design. Okay. Okay. So this is some TLM port. I'll explain it later. Right now it may not easy. Okay. Now, right, what happens in your UVM, right? In UVM we have something called phasing. What it phasing means? What happens at each phase, right? We have something called build phase, connect phase, run phase, and then we have final phase, right? What happens in each phase? Say for example, in the UVM, I have something called, as I said, right, agent, I have, right, monitor, driver, scoreboard, I have multiple things, right? I need to build each thing. So that build will happen in the build phase. Okay. And then I need to connect each component, right? That connection will happen in the connect phase. And then I need to run the test case. The test case run will happen in the run phase. And the final phase will get your output and compare the output, will give you any error or something that will be in the final phase. Okay. All this, I think I'll show you in your environment, right? Okay. This is how the actual architecture will look like, right? So whatever we saw so far will be there in this entire one picture, right? Let's see how this picture, right? As I said, this picture will be common for any IP you take, any SOC you take, anywhere you go. This will be a common one. Okay. Say we have a design, and this DUT can be anything, can be an IP, can be an SOC, anything. Now, there will be something called test. Okay, so we have UVM test bench at the final layer. Internal to that test bench, we have something called UVM test, right? So all the test cases will be here in the test layer. Next, we have something called agent, right? And then we have something called sequencer. And inside the agent, there will be driver, monitor, all those things. Okay. So this one, I think what I'll do is I'll draw this and I'll explain you, right? That will be good. I'll open a new one, right? See, for example, just excuse me if my drawing is not good. I'll just show you, right? Okay. I'll just show you how it looks like, right? So we have something called my design. Okay. So I have some DUT, right? I have some DUT here, design under test. So what I have, right? This is my environment. So inside the environment, see, basically what I'm going to do is I'm going to generate some stimulus. I'm going to give to my device under test, right? I'm going to give it. So for that, I have something called environment. Okay, so there will be something called, this is something but your env. Okay, so there is nothing but env. This is environment. Inside this, I have an agent. Okay, I'll put an agent inside this. All this, right? I'll show in the code how it is. Okay, I have some code for this. I'll show that code also. Okay, what will be there in each code, right? I'll show everything, right? But before that, I'll give you a picture how it looks like, right? Inside my agent, what happens? What all I have is I have something called driver. Inside my agent, I have something called driver. This is driver, and then I have something called monitor. Okay, so I have something called monitor here, and then I have something called sequencer. Okay, this is your sequencer. Okay, there is something called sequencer, and I have something called sequence. Okay, I'll put it here. It should be outside this. There will be something called sequence. Sequence. Okay, so what happens, right? Okay, so what happens from my test case, right? I'll run the test case. So the test case will call a sequence. Say, for example, it's a memory. This DUT is memory. I'm going to write and read to this, right? How will I write and read? For write and read, I need, for example, I need address and data to write and read, right? So what address I want to write, what data I want to write, that will come from my sequence. Okay. So from my sequence, it will be, the sequence will be running to the on the sequencer. Okay. It will run on the sequencer. This sequencer and driver will be connected. I'll show in the code later how it is all done, right? So the sequence and driver will be connected. From the driver, there will be an interface which goes to the DUT. Okay, there will be an interface. Okay, there will be an interface. Same way, there will be interface to your monitor. Now, this is a simple, okay, very simple way of giving a UVM flow, right? So a test case will run. In my test case, I will call my sequence. I call write sequence. What it will do, it will run on the sequencer, and then this sequencer, what it does is, it will, whatever address and data generated from this sequence will go to the sequencer, will go to the driver. This driver will drive to the DUT. Say, for example, address equal to 10, data equal to 5. So it will go to this memory. So at 10th location, it will write address, 10th location will write the data 5. And whatever is written, right, it will, monitor will get the data, monitor will store that inside my monitor, it will store the data. And later on, I'll check the data from the monitor, right? I'll read, next I'll run a read sequence for the address 10. That will again come from sequencer. It will go to the sequencer. From the sequencer, it will go to the driver. Driver will give the read command, means address, read with address equal to 10. The output of the DUT will be data. The data will come as 5. It will be stored in the monitor. And I can compare those two. Okay. So I can do that in a monitor, or I can have something called scoreboard. Here I will have a scoreboard which will compare the data, write and read data, whether it's same or different data. If it's same data, it is fine. If it's a different data, it is an error. Okay. So this one, right, I will show with an example now. Okay. So for that, I generated something in my EDA playground, right? You guys also can have something called EDA playground. You can go to the EDA playground and you can register. This is a free tool where you can do anything, whatever you want, right? Okay. So I'll just explain you, right, how it works. So for that, I have taken this memory model, right? Example of memory model. So what it does in the memory model, right? What it does, it gives address, it gives a write data. You can give input as address, you can give the input as write data. it will write. If write enable is 1, it will write into the memory. If read enable is 1, address whatever you give, right? Output will be a read data. Okay, so that is what it is. So this is a Verilog code. If you see here, you would have written that if write enable is 1, you will write the data to the memory. If read enable is 1, whatever data is from the memory, you will go to the read data variable. It will go to this variable output, right? So this is what it is. So here you have this input as address, the write enable, read enable. Input is W data, output is R data, read data is the output. So this is the circuit. Okay. Now this is a design. I'm going to verify this design, right? So how I'm going to verify this design, as I explained here, right? I'm going to verify like this. How I'm going to do that is, let me show you, right? So I'll go with the basic one, right? I'll go with the test case. I have something called test. This is what the basic test case looks like, right? I have some test class write read test. What it is going to do, it is going to have a sequence, right? Write read sequence. Okay, so we are instantiating the sequence. So to what it does, that's why I said you need to know the concept of your OOPS concept, where this sequence instantiated here. If you instantiate a sequence, what happens? That will come from your write read sequence. Okay, now you have a write read sequence. So what happens? I need to start this sequence to run, right? So what happens in my run phase? I will do something sequence dot start. What I'll start env agent dot sequencer. I'm going to start this sequence which is there inside this sequencer. I'm going to run this. Okay. Now, as I said, the phases, right? You will remember, right? I showed you the phases for your UVM, right? So you will have something called new phase, build phase. Connect phase is not here. Connect phase will come in another in the agent. I'll show you. So what happens in the new phase, right? This is nothing but your, as I said, right? In C, whenever you declare anything, you should have a constructor, right? That is being done here. Okay, this is the new phase. It's nothing but your constructor. Okay, this will create the sequence. I am declaring the sequence here, right? After declaring the sequence, I need to create the instance of the sequence, right? That instance of sequence is created over here. Okay, so we create using this method. So this create, right? This method, right? Whatever is a type ID, create, this syntax, right? This is built in the UVM. UVM comes with a lot of built-in macros. So you no need to go and do everything by your own, right? It's all there. What you want to do is you have to use it and you have to use it for your application. What I did is this sequence, right? This is my sequence for my application. I have this sequence. So what I do is I just instantiate the sequence here and I'll create the memory, right? So that instantiation is done by type ID create. This will do that. Okay, I'll use this inbuilt create method and then I'll create the sequence. And in the run phase, what I do is I'll just start my sequence. Now what happened as per this diagram, we started the first thing. We just started the sequence. Okay, now this sequence has to generate me the address and data, right? Address and data has to generated from this sequence. It has to go to this memory model. So for that, we'll go and see what is there inside my sequence, right? Okay. So before that sequence item, I'll show sequence items. What are the sequence item we have? Whatever the variables, right, that will put inside a class called sequence item. Okay, we have something called sequence item. What all we have here? Address, write enable, write data, read data. Okay, and all this I'm putting as I explained, I'm putting as rand because I cannot give any particular address, right? It can be a random address, random data, right? So I'll put all the random variables here. Okay, and what all this is, right? It's a big concept. I'll let you know later, right? So if you have time, you can go and see what UVM all on means. Say for example, UVM all on means this variable, right? Whatever I'm giving address, for example, address, right? This variable can have like built-in functions, right? This can do copy or you can do a print, you can clone. There are multiple built-in functions comes along with UVM, as I said. So if you read UVM in deep, you will come to understand what are the different functions it has, right? So I'll put UVM all on means I can use all the functions of my UVM here for this variable. Okay. Then I have the same new class. Then I have a constraint. What constraint I have is I can get any address, I can get any data, I can get anything. But what the constraint is, my write enable and read enable cannot be same in the same time, right? I cannot write and read at the same time, right? Either I have to write or either I have to read. If I don't give this constraint, right, what happens? Write enable will be one, read enable, it is random bit, right? So there might be a scenario where write enable will be one, read enable also will be one. So that's a wrong scenario, right? I cannot do that. if it goes to design, write enable, read enable, right? What happens here? It will not execute. This will be one. This also will be one, and it will the design will not work, right? It will go to a hang state. It don't know what to do, either write or read. It will go to hang state. If you take your any application, right, your laptop or phone, right, it gets hang because of like this only. There are some issues where you give multiple, when you do two or three things at the same time, right, you get a hang because you don't know which one to execute first, right? So what I am making sure is, I am making sure from this constraint you can generate write enable, read enable randomly. I can generate any value 1 and 0, but I am making sure at any given point of time both are not same. Write enable and read enable are not equal. Okay, so which means when write enable is generated 1, read will be 0, or when write enable is 0, read enable will be 1. This will be taken care by the tool when I write this constraint. Okay, these type of advantage, right, you don't get in your Verilog, you will get in the system Verilog only. Okay, now here also there's one more concern, right? How much, like you run 10 times, right? Out of 10 times, how many times you want to have write, how many times you want to have read, that also you can give. Which is more priority? Write is priority more, or read is priority? Or you want to make sure write and read is 50-50%, right? You get 50, read also 50. All those you can add by writing some more constraints. You can do all those things. Okay, for now I'm just giving. Now what happens, this sequence is there. Now what happens, we need to this rand, right, it will not generate the value by itself. When this will generate, it has to be randomized, then only the value will be generated for these variables, right? So where it gets generated, that is generated inside your sequence. You remember, right? In the test case we called a sequence, right? What the sequence we call? Write read sequence we call, right? This sequence, what is this? This will be available in your mem sequence file, right? So here if you see, we have something called sequence item. You create that, and then I'll explain this. After this I'll explain this. I'll come to this 3-4 line code. Okay, I'll show you what happens. Writes, what is a write sequence? Okay, so write sequence is nothing but you call your UVM do with write enable with 1. So what is request is nothing but, from this diagram, this request is nothing but the arrow mark what I have drawn, right? This sequence will go to the sequence. This sequence, right? Sequence item is coming to a sequence. So this is, sorry. So this is nothing but your sequence request, means from your sequence item, the request will come here with, you are going to constraint, right? This is what it is. Do UVM do with what constraint you are giving? Write enable equal to 1. Okay, we are constraining to write enable to be 1. So when you constrain write enable to 1, automatically read enable will be made to 0 in this sequence. Okay, likewise we can have read sequence which is going to have read enable, same thing, but read enable to be 1. And then we can also have something called write read. This is going to execute only write, this is only read. We can have both write and read also, right? So what happens, first I will have write sequence, write enable dot 1, or can I have write read enable dot 1. This also I can do. There's another way of doing it, which is nothing but I call the write sequence separately, I call the read sequence separately, right? I'll just start those sequence. UVM do write sequence, UVM do read sequence. If you see here, we are doing UVM do with, whereas here we are doing only UVM do. Why? Because here we are doing UVM do with, we are giving the constraint, right? Write enable should be 1. We are giving this constraint here. Whereas here we are not giving any constraint. Why? Because we are running which sequence? Write sequence. What is this WR sequence? WR sequence is nothing but the write sequence. Okay. So if you go to write sequence, it will run this sequence, write sequence. So here if you see, that will be taken care here. Okay. This is called reusable. I will not do this every time. I'll just have this one time and I can have it multiple places like this. I'll start this. Okay. Now from the test case, you remember what sequence we started? Write WR underscore RD underscore sequence. This is the sequence we wanted to start, right? This sequence is a sequence we are instantiated here, SEQ only we are starting right here. SEQ dot start we are doing, which is nothing but WR RD sequence. This WR RD sequence is nothing but your WR this sequence, right? It is going to start this sequence. What it mean by start? Means it is going to run this. So when it's going to run WR sequence, what is WR sequence? It's nothing but write sequence. What is this write sequence? It is nothing but it is going to give random address, random data with write enable as 1. Okay, so now this is being given to your sequencer. Now what it has done, it is given to your sequencer. What sequencer has to do? it has to give to your driver, right? This has to be done. It has to give to your driver, right? So what we do for that is, see here, we'll go to a driver file. We have to write something called driver. So we have something called driver, mem driver. Okay, mem driver extends from UVM driver. So same way we have to instantiate here, right? Constructor for the driver, and then we have to build the driver, build phase, right? What we are going to do in the build phase, right? We need in the driver, if you remember in the diagram, right? We have something called interface, right? We have this interface. This interface has to be there in the driver, right? So what I do is I instantiate that interface. Void build in the build phase. I have this interface. Okay, mem interface. Okay. So what is this mem interface? Mem interface nothing but if you see here, I have something called interface file, right? Mem interface. Okay. Mem interface nothing but I have the interface signals: address, write enable, read enable, write data, read data. These are the interface signals, right? What all I have here, right? So I'm going to drive address it to this, write enable to this, read enable to this, write data to this, and read data will come in this variable, right? So that will be your interface that you have in your driver part. Okay, so you have it in your driver. Now what we are going to do is I'm going to have this function, right? Sequence item port dot get next item. This is a built-in function of a UVM. As I said, right, there are multiple functions inside UVM. They are built-in macros. That's why we go for UVM, right? Many things are already available. You're going to use it. One of that is sequence item port dot get next item. What it is going to do is this is going to tell I'm going to get the next item from my sequence. So this driver is going to get the item, whatever item I have from the sequencer, this driver is going to get. So what item the sequencer has, that sequencer has, or we saw, right, the sequence what it has, write read the sequence, right? It is going to have a random address, random data, and write enable as 1. This is the value it has. That value will come to your driver part. It will come to your driver part. Okay. After getting those values, that value has to go to the duty, right? It has to go to the duty. How it will go? There is a function task called drive task. What this drive task is doing? Drive task, if you see here, go to the drive task. It is going to drive address. This interface is nothing but that what I showed you, right? That interface. So interface address is nothing but what address we got from this random address, right? That address we will get it over here. That address value will be here. In, for example, if you generated random address as 10, that 10 will come here, that 10 will go here. And then write enable, in our case, we made write enable as 1. So write enable will be 1. Write data, random write data. For example, write data is 100. The value of 100 will go. This will go to your DUT. Now what happens? You have a sequence, you generated the random values, you connected that in the driver. Now the driver is going to drive here. It's going to drive here. Address is going to be 10. Write data is 100. Write enable is 1. It will go to over here. Like this, we will run for multiple test cases. Multiple sequence will be run, and every time we will get some values, different address, different data, different write enable, read enable, all will give to this memory models. Okay, so this is a driver will do. Now I see, for example, first value I got it from the sequencer. It's like a queue, right? It's like a queue. This will generate me 100 times. It will give to my sequencer. This will give to my driver. First value it's given 10, address 10, data 100. It is given here, and then it cannot give the next value directly, right? First value address 10, second value address 20. It cannot give. It has to wait for some time till the value whatever it got over here. It has to go to the duty, right? Then only it can get the new value. If I don't wait here, right, what happens? I get 10, I get 20, I get 50, right? This value will get overwritten, right? It cannot go to the duty. So I got some value, I generated some value. I need to test for that value. Address 10, write data 5. I need to do that. So I got that. I pass to the duty, right? So that it takes some time for that function to happen. So till that time, it has to be in the wait state. This has to wait. So how this has been taken care? This is taken care through this statement. Sequence get next item. In my sequence, right, I said, right, I'll explain those 4 lines later. So what it does, first step is it will randomize it. Request dot randomize. It will randomize the address, data, and everything. Send request means it will send that first randomized data. It will send to the driver. Now, after sending that, it will wait for the item done. It will wait from the response from the driver, whether the driver has sent all the data to the duty, because sequencer doesn't know. It knows it gave to the driver, but whether driver gave to the duty or not, this sequencer doesn't know. So it will wait for the response from the driver. That response is nothing but in the driver. After I am driving it, I'll tell sequence item port dot item done. This is also a predefined function in your UVM. I'll tell the item done, which means my item is done. So I can get the next item from the sequencer. So whatever it randomized, right? It will wait for here. Once it is done, it will again come, again do the randomize, again send the data. Again here we are repeating for 2 times. Means it will do for 2 times. Address data, write enable, wait for that write enable to go to the duty. Next again it will come here. It will address random data, read enable, then it will wait. So it is done for 2 times. Like this we can do it for 100 times. N number of times we can do it. Okay. So now the data has been driven to a duty. Okay, so what we have done now is we are given we generated the address, we generated the data, we give to the duty. Is that functionality like what is next? Our verification is done? No. I have returned something to the memory. But whatever I return, whether it is actually correct or wrong, how will I come to know? I have to read that from the memory back. I have to compare the data, write data compared with the read data. Then only it will know whether it is done or not, right? So how will I do that? I have something called monitor. Okay. So I'll go to the monitor. What I do in my monitor, right? Same way I have some monitor. So this has again the interface, which will I show you, right? Monitor also has this interface, right? So that is nothing but your interface. Then what I do is I will have something called run mem sequence item, right? What are the sequence item I'm going to collect? That sequence item. Basically, what it does is, see, it will wait for write enable or read enable. This is nothing but the output stage. It will get the whatever is at the duty, right? I will monitor that. Means I'm going to get that signal from that interface, right? If write enable or read enable is toggled, either of the thing, then I'll put address. If write enable is there, I'll put the write data. If read enable is there, I'll put the read data back to my monitor. And from the monitor, I will connect to my scoreboard. Okay, so I have something called scoreboard. From monitor, scoreboard, we have same thing build phase. I will build that. And then in the connect phase, so that will be there in our agent, right? Right. In my agent connect phase, right? I'm going to connect driver and sequencer. Okay, I connected the driver and sequencer. So this connection, right? The driver and sequencer I connected, right? This is done in my agent. Where is it? Okay, so this is done in my agent. I connected it. I got to connect the monitor to my scoreboard, right? I have something in the monitor. This monitor has to go to my scoreboard, right? This has to be done. So how is that done? That monitor to scoreboard connection will happen in my env. That is my env file. Yeah, env file. I have something called connect phase. I connect monitor dot port connected to scoreboard dot export. So I connected over here. So now what happens? Whatever data I'm getting from the design, right? I'll get in the monitor. I'll put the data into my scoreboard. After putting in the scoreboard, I need to compare the data, right? What I do is, see here, I get that packet. Then I'll get that packet. Here I will compare that data. My read enable is 1, means I get the read data. Once I have the read data, I will compare whatever I written in the address is same as whatever I got from the duty. If both are same, then I can say read data match. If it's not same, I will say read data mismatch. Okay. So like this, we will do it for any logics, right? So we'll have something in the scoreboard. So basically this UVM, this is structure, right? I showed you each one is to be done, right? I can write this driver code inside my sequencer. I can write it, or inside my sequence, I can write whatever is written inside this code, right? This particular code I can write inside my driver file. I can write over here. Still it works. But what happens? We cannot do that because UVM says you have to follow a proper structure. So we'll do like this. Okay, we have to do everything has to be done in each thing. Okay, each component. Driver means it has to only do the driving component. Monitor means it has to do only monitoring. Scoreboard means it has to compare it. So like this, we have to do it for each place. Once you have done it, right, we can run this, right? I'll just run this and I'll show, right? You run this code, right? Your entire memory model, you are running it now. So we have finished, the run is finished, right? So if you see here, there are 14 info, there is no warning, there is no error, there is no fatal, right? Okay. So now we see this one, right? The log file. So here if you see, right? Okay. So what all it generated, randomly it has generated, right? What all it generated, address 0 is generated randomly, data is generated C4. Okay. Now I'm going to read data. Then it has done that. Then it has matched the read data as correct. Then it has generated address 3. Expected data is FF. Actual data is also FF, which means the data is matched. Like this, we'll do for n number of times. We can do this. And this is an example of a memory model, right? Small memory model. But if you go in the real time, we have multiple things. We will do it, right? And I'll just show you one small thing from my project, right? Real time project. Well, the coverage, right? How it will be happening in the real time coverage, right? I'll show one thing, right? Okay. So this is a coverage report, as I said, right? Coverage report, functional coverage, right? Here in this module, right? Between a module to n module, inside my one of my module to n module, right? I have so many signals. Okay. So these are all the signals I have. Now I have written my, we are in a state in our project, we are running multiple test cases multiple times, and this is the values we getting, right? Say for example, I will go to this variable, right? For example, this variable, what happens? This has only the value, it can take this particular variable, right? It can take only the value of 1 by 16. So what happened? I have run 200 times, 209 times I have run. I got this value. So this is 100%. My coverage is done. But whereas if I go to this particular variable, right? This particular variable can take two values, 1 by 16 of T1, 1 by 16 of CT1. It can take two values. But so far in my verification, right? So far, whatever test we have ran so far, right? Every time it has 24 times we have run this test, and all the 24 times it has generated only 1 by 16 CT1. 1 by 16 T1 has not even generated one time also, it's zero, right? So if my manager sees this report, right, he will check and he'll ask me, right, why you have generated only 1 by 16 CT1, not T1? This value is not generated. If I don't generate this and if I leave it out, right, tomorrow when the chip comes out and if this value is generated, then we might be a buggy. So what I need to do is I need to run my simulation more, random simulation. I need to generate this particular value, and I need to make sure for this particular value also the test should have been passed. Then only I'll get the count here. Like this, I need to get the count 100% for all the variables. Okay. And there are few variables, right? So far we have never hit, right? These values we never hit. It's all zeros only. Never we got that. So which means we are missing that, we are missing these scenarios. So we need to run these scenarios. That's what it means. So I will do like this. Same way, this is for functional coverage, right? Like this we have for code coverage, right? I'll show, right, a small code coverage. So this is another module where we have so many signals inside my code coverage, right? So many signals. And this is a toggle coverage, right? What we want to do is every bit has to go from 0 to 1, 1 to 0. So this toggle has to be covered. Why? Because if you measure only 0 to 1, and if you don't check for 1 to 0, right, then it will have some stuck at 0 fault or stuck at 1 fault. So all those things you have to verify, right? So for that, what we do is we make sure that all the bits have all the toggles 0 to 1, 1 to 0, right? So far in our this is the current live project what I am doing, right? This project is ongoing. At today's stage, this is the status, right? So currently, if I see this particular signal, right, STAP IP port ID, right, this particular signal doesn't toggle in my simulation. It is always zero. This input is always zero. I never gave any of the value, right? It has to go, all the 16 bits has to go to 0 to 1, 1 to 0. That toggle has to be done, but never I hit. So I need to generate. For example, this variable, right? CAB enabled. This variable, I have in my test case, I already covered 0 to 1, like 1 to 0 it is hit, 0 to 1 is hit. So toggle coverage is 100% for this particular variable. If you see, there will be some variables, okay, where there won't be any toggle from 1 to 0, but 0 to 1 will be done. So like this. So all those things, right? At the end of my project, I want to make sure I have 100% for all the signals. This is for only one module, right? Like, see, if you see, there'll be hundreds of thousands of signals here. This is for only one module. Like this, we have n number of modules. and for every module, for every signal, I need to make sure that code, it has been covered, all the toggle is covered, as well as the functional coverage, right? It has all the functional bits have been covered. Only then I can say 100% of functional coverage, 100% of code coverage. I can say to my boss, okay, boss, I have done my code coverage, I have done my functional coverage. I am very confident my my design is 100% error free. Even though there might be some error will be coming from the real time scenario, which we may not predict, but still we have a confidence. Okay, we have verified fully. Okay, without this, we will never close the project, right? So this all we do at the part of our verification, right? This all we do. Okay, so this much I have planned for today's session. If anything, like any questions you guys have, I think we can. Because I have given very, like, I don't know, I went very fast also. So if anything, we can discuss any Q&A. We can discuss here. And if you want to learn more, you can always go to this platform, right? EDA Playground, right? You can go to the Google, you can search for EDA Playground, right? This is a place where the tools are free, where you can practice your own thing. You can create your own file, new file. You can write anything, and you can start verifying. You can simulate, you can check, and you can do it, right? This tool is free, so you can practice in this tool. And you can also select what type of tool you want, synopsis, cadence, all those things you can select from here, and you can do whatever you want, right? So this will be very helpful, EDA Playground. Okay, so any Q&A, we can discuss it. I think I've ran fast, but still. Any questions?
Participants, if you have any questions, you can unmute yourself and you can ask, or you can post your questions in the chat box too.
There's no questions so far.
Thank you so much, sir.
Yeah, I'm not, like, I don't know how much people
Yeah,
have
your
asked it.
presentation is very good, and we got it's very informative, sir. Thank you so much.
Thank you, ma'am. So if
I
anything is doubt, I can, if you want, I can share this presentation, but I cannot
sure,
share my code and all. I cannot share, but this presentation I can share. And if anything is there, you can check it and you can come back. If anything,
sure,
you
sir.
can email it. I
Definitely,
can
that I can
explain.
do, sir.
I can explain you guys.
Now I invite Ms. Sendil Priya to deliver the vote of session for this session.
On Department of EC and R.M.D Engineering College, I thank Manikandan sir. Thank you, sir, for wonderful session and the hands-on you have taken. It is very well and it is very interesting for the participants too. Thank you so much, sir, for the experience shared here and joining us. Thank you so much, sir.
Thank you, ma'am.
Thank you, sir.
Thank you, ma'am. Oh, yeah. So we can drop, right?
Yes, sir.
Thank you, ma'am.
You.
Thank you, ma'am.
Dear participants, I thank you all. I open this forum for feedbacks. One or two can give the feedbacks for the 6 days program here.
Hello, ma'am. This is Rajendra Kumar. Can you hear me?
Yes, sir.
Yeah. It was a great FDP, and I could see many information which we have gathered from all the NTPL and all the speakers, and particularly till now up to date, I have been attending many FDPs or something workshops related to things, but I couldn't find something which is informative related to neuromorphic computing. And with respect to your FDP by RMK, and especially I should be very thankful for the coordinator as well. I think you are one, ma'am. Yes, isn't it, ma'am? Vanilla, ma'am.
Yeah, I'm Benila. Belongs to
Thank
R.M.D.
you so
Engineering
much
College,
for
sir.
thank you so much for the conduction, and it was a great session and great meeting you as well, ma'am. Thank you so much.
Thank you so much, sir. Thank you so much for your words.
Good evening, ma'am. This is Dr. Pooja Saxena, and I am from GNIT Institute of Technology, Greater Noida. And my research has been in VLSI domain only. So, and in future also, I was planning to do a research in VLSI. That's basically paved me to join this FDP. And as per my perspective, this FDP has been proven me a very good platform for me, because it introduced all the VLSI design levels, like starting from semiconductor technologies, from fundamental to the next generation VLSI design flows, like digital design flow and hands-on experience using Cadence and Innovus design tools. And most importantly, it basically gave me the insight of application of AI ML algorithm at various levels of VLSI design, so that I got aware of how we can go ahead for data driven hardware optimization as well as the verification. And the most important part is the resource availability. As in VLSI technology, whatever idea we have, but if resource is not available with us, then we cannot do anything. So that was have been a bigger challenge for me, that got solved through this FDP only, because Shiv Prasad sir and Jaya Lakshmi sir, madam, they only introduced this thing, like cloud based tools are available also, that we can access, and open source and AI driven tools are also available, so we can carry on with the help of these tools. And Dr. Noor Mohammed sir, he introduced how we can apply the ML algorithms at various levels in VLSI design, may it be at the gate level, RTL level, or automatic PNR level. So there are various levels where we can introduce these algorithms. So through these insights, basically, I all the sessions have been a very much informative for me, and because of that, I'm very thankful to all the speakers, and to you also, and because you only organized this FDP and arranged such a good speakers for us. So I am very thankful to you as well as the speakers. Thank you, ma'am.
Thank you so much, Pooja ma'am. Thank you. Anyone else wants to share?
Hello, ma'am. Am I audible now? Hello.
Yes, sir. You're audible, sir.
First of all, good evening to one and all, ma'am. And I'll make a quick brief of all the overall FDP, ma'am. I'll not take much time. As a research scholar, maybe because I'm in one of the late stages of research, but as a research scholar, I found the theme, ma'am, like the next gen VLSI and machine learning was timely and relevant for my work and my research works, because which I was planned, and the content was perfectly structured, and progression from core concept to advanced applications was very crystal clear for me. And the highlights for me was the outstanding mix of speakers. That's like having distinguished professors from institutes like IIIT, and IIT, alongside industry leaders from companies like Intel, Thales, and Intuple Technologies, provided a complete perspective of this FDP. And of course, none of this would be possible without the organizers. I want to extend a special and personal thank to you, the coordinators, Dr. C. Benila ma'am and Ms. Senthil Priya ma'am, for their flawless execution and for making this a smooth and enriching experience for all of us. So overall, it was a fantastic week, and I'm also looking forward to conduct FDPs for my institution. So I look forward the participation of the same team also over there. So once again, thanking you everyone and wishing you all the very best.
Thank you so much, sir. We'll be happy to help you, sir. Thank you so much. And thank you, participants. I'll give some instructions regarding the certifications and assessment. Once the session is over, after the closure, I'll post the assessment link. Google Form, we are going to conduct the assessment. I'll post the link through the WhatsApp as well as WhatsApp group as well as the mail ID, registered mail ID. Kindly take the assessment before 8 o'clock, and then you just give the feedback in the Atal portal also. So it will take 2 to 3 days to update your attendance as well as your assessment marks. So once the assessment marks and the attendance has been updated in the portal, and once if you take your feedback, if you give your feedback in the Atal portal, then you will be able to receive the certificates. Kindly bear with us for at least another 2 to 3 days to get the certificates, and if you have any queries regarding that, we are happy to help you. We'll be available online, so you can take your queries in the WhatsApp group also. Thank you. And I'll propose a vote of thanks. Good evening, everyone. It is indeed a great honor and privilege to deliver the vote of thanks of this AICT sponsored faculty development program on next gen VLSI and semiconductor systems integrating machine learning for intelligent design automation. From 3rd November to till date, for 6 days, we had an intellectually stimulating journey exploring how the synergy between machine learning and VLSI design automation is shaping the future of semiconductor technologies. First and foremost, I extend my sincere gratitude to the AICT Training and Learning Academy for granting us the opportunity to organize this FDP. Their continued encouragement and support towards faculty development, research, and innovation are truly commendable. I express my heartfelt thanks to our management for supporting us in all the activities we do academically. I take this opportunity to convey my deep sense of appreciation to our beloved principal, Dr. N. Ambachalian, for the constant guidance, motivation, and administrative support in conducting this program successfully. Our department head, Dr. Helen Prabha, deserves a special thanks for her unwavering encouragement and cooperation throughout the FDP. I wholeheartedly thank our distinguished resource persons of all 13 sessions who made this FDP a truly enriching experience through their expert sessions and interactive discussions. Their contributions have provided a valuable exposure to cutting edge developments and opened new avenues for collaborative research. And a big thank you to all our participants from various institutions in various levels like PG students, research scholars, and teaching fraternities across the country for your enthusiastic engagement, curiosity, and active participation in discussions and hands-on sessions. Your involvement has made this FTP truly interactive and rewarding. I also extend my sincere appreciation to my team, Ms. Sindhil Priya, Mr. Jai Ganesh, and my student volunteers, Ms. Srinidhi, for their dedication and tireless efforts in ensuring the smooth conductions of this event, right from planning to the successful completion. We, R.M.D. Engineering College, is ready to help you guys at any manner. Last but not least, I thank everyone present here for your support, cooperation, and positive energy throughout that FDP, keeping the dignity throughout in the forum, and let us take forward the knowledge gained here and continue to innovate at the intersection of machine learning, VLSI, and semiconductor systems to build a smarter and more sustainable technological future. Thank you all once again, and I wish you continued success in your professional and research endeavors. Thank you all. So we close this session. Thank you all participants.